All right, 11:05 now. Let's start. Good morning, everyone. Welcome back. Welcome back to CSE 545 Software Security. And this week, we are going to talk about reverse engineering. I know that many of you have watched the video. Like in my YouTube, I guess this is the nice thing of having a YouTube. You can track the number of reviews over there, and I can definitely see how many people that have clicked this link and watched the video, and that will give me a very good like a feeling for how many of you have watched the video. And I do see a pump of you know increasing numbers for the video watches comparing to last week. So I'm very happy that many of you have watched the video, which is great, and that is going to be very helpful for you to fulfill today's lab and also futures assignment. So again, similar to what we have had in the last week and in the first week, we're going to go through the logistics a little bit, because I know that some of you still you recently joined and you may still don't have a clue of how this course work. And I understand that because of in COVID-19, every course is working in a different way. So I'm gonna spend a couple more minutes to re-emphasize or say to recap our logistics, and then we can move on to today's lab. So again, this is the links that you will need for this course. I will put course content in the website. It has the slides. It also has an assignment. Also, there is a YouTube list for the course videos. I put all the videos over there, and usually before I upload or before I release videos, I will let you know through Slack. And you need to join the Slack in order to get those announcements in time. And someone is asking me if the videos are complete. The answer is yes. For this week, the video is complete. And there will be more video coming up probably in the end of this week or at the start of next week. But that's for week 4. And then in class, we are gonna have this, we're gonna use this Zoom recursively. Sorry, I mean, what I really mean is not recursive, I mean repeatedly, into the end of the semester. And I assume that you already know it. That's why you are be able to join this class and listen to me right now. And also we're having another office hour link where you can ask questions to me, to me or to TAs. And the regular office hours is going to be all on Thursday, and I intentionally make it one before and the other is after the in-class lab, just in case that you have any questions on the lab. You can just go to the link and then ask us questions over there. All right. So today I am going to try to use both monitors because I want to, write to annotate some of the screen content. So this is the first time that I'm trying it, and I may miss some of the chat from you, or I may just have totally messed up the equipment. Give you a heads up. So if I happen to do something wrong, please let me know. Or if I miss any of the chat questions, also just let me know. You can just unmute yourself and ask me questions during the lecture. So we have finished the first assignment. Um, you can still submit via response. You can still, submit the form, but I already downloaded the form content. So it's kind of done over there. The new submission will not be counted. And we will start grading based on your score and your response in the form. And we will announce your grade later on when we finish, and we will announce it in Slack. So stay tuned in the announcement channel, and we will let you know once your grade is available. All right, so today we are going to have, again, a lab together. And let me go to the lab page. It's here. So today we're going to have a new service for you to play with. And this service is majorly for you to have a quick warm up on Exodus 664 assembly. So this is the service IP 107.21.135.31. And the port number is 3000. And similar to last time's lab, you can connect to the server using Netcat or whatever way you'd like, and you can play with over there. And you will need to provide your ASU right ID because you will need that for your participation and future assignment. And let's start with challenge assembly 0. So here, let me share my screen with you very quickly. All right, let me just go to course. And again, the IP number is, actually, I forgot, but I can just pull it out. It's 107.21.135.41. Let me zoom this out a little bit. Hopefully you guys can see this very clearly. So this is the IP number, and this is the port number. If you do a netcat, you'll be asked to input your ASU, right? And then you're going to be started with 5 challenges. And in today's lab, let's start with the first one, which is called Assembly 0. So you will be able to see the question in your screen. And they will ask you, what is the result? What is the values of 2 registers, EAX and ECX, after running assembly 0 as a function? Now I'm going to give you a couple of minutes to log into the service and play with this challenge. And if you do know how to solve it, just type your answer over there and it will tell you whether or not your answer is correct. All right, I'm going to have a, say, 5 minutes to 10 minutes and for you to play with. And if you have questions, you can just ask me now.
Professor, can you show me the IP address?
Yes. The IP address is 107.21. Let me zoom this out again, and then you guys can always see the IP address from this screen. It is right. So I get questions from you guys. In terms of the values on the left, those are the address numbers. Those are the address of the instructions. And in terms of which registers are ARGs loaded, this instructions, this program is complied with the x86 64 calling convention. If you don't know about calling convention, that's okay. You can Google it, or actually, I'm going to talk about that later. You can also just wait for me to talk about calling convention later on. All right, guys, I'm gonna start. I saw many of you have accomplished this level, and even and some of you even have accomplished the next level, Assembly 1, which is amazing. Good job. So now I'm gonna have a very not brief, but I would say like a quick walkthrough on this challenge. And I hope that, for those that don't know too much about calling convention or the details about of x86 64, I hope that my walking through will help you understand this challenge and also, more specific on x86 64. So as you see in the screen, now we're gonna look at this assembly. It's called assembly 0 with the argument arg1, arg2, and arg3, right? And many of you have asked me this question. Many of you are asking that, where does those arguments store, right? And the answer is that according to, sorry, give me a second. Let me go back to my screen. Okay. So according to the calling convention of x86 64, the arguments are gonna be stored in registers and stack. And notice that this is different from x86, like the 32-bit instructions, because in 32-bit instructions, all arguments will be saved on stack, whereas for x64, some of the arguments are stored in register. And specifically, maybe this yellow is, let me change the pen's color because the contract is not very well. Okay, this is nice. So arg1 will be stored in register RDI, and then arg2 will be stored in register RSI. arg3 will be stored in RDX. And then for complete view, the first 6 arguments will be stored in register. So they're gonna be RDI, RSI, RDX, and then followed by RCX, and then R8, and then R9. So this first 6 argument is gonna be stored in registers. And starting from the 7th argument, if there is a 7th or more registers, arguments, it's gonna be stored in the stack. And now we need to talk about the stack, and let's take a look at the stack. As I mentioned in the course video, stack is, you can consider stack as, like a big chunk of memory, and then the lower address, like the address is gonna be rising from low to the high. And then for stack, when we do push, it's gonna be pushed to the bottom, which is like the lower address. Usually, if we have, a function, the function may save some registers or save some values at the beginning of the function, and in those cases, it's gonna be doing like push or pop operations. If it's a push, then it will push the last part of the stack. If it's gonna pop, it's gonna like take it out, and then this content will be disappear. And the way that computers track the bottom or say the base of the stack is to use register RBP and RSP. RBP means the base of the stack for a function, and then RSP usually refers to the bottom of the stack. Okay, and then in this case, there's no push or no pop. There's no such, like stack related operation. And we're gonna just look at the assemblies, look at the registers, and keeping in mind that the arguments here are gonna pre-saved into this 3 register. RDI, RSI, and RDX. Okay, now let's look at the code together. So when I look at the code, I usually start with the question of asking myself, which syntax is it using? Because sometimes we will use Intel syntax, sometimes we will use AT&T syntax. And it is very important for us to know which one is, which syntax is using so that we can know which part of the operand is the destination operand and which part of the operand is the source operand. So for this specific example, can someone tell me which syntax is it using? Yes, I see many of you are replying me on chat. That's great. Yes, you're all correct. This is Intel. And one way that you can tell whether or not this is Intel is to look at the representation of register. So usually for Intel, if you represent a register, you don't start with a percent sign. But for AT&T, if you want to represent a register, you usually want to have a percent sign, like percent EAX or percent RAX. Okay, great. So now we know that this is Intel. And now let's start with the assembly. So the first one is the move statement, right? Move EAX EDI. So it means that since this is Intel, EAX is the destination register. So you're going to move the value from EDI to EAX, followed by this flow. So what is the value of EDI in this case? Can someone tell me in chat? Nice. Yes. So this is 78. And this is because the first argument of assembly 0 is 78. And EDI, as I mentioned before, for calling, according to calling convention, stores the value of the first argument. So here, it's actually going to move the value of EDI, which is 78, to EAX. So now the value of EAX becomes 78. Now, actually, give me a second. Let me change the color of this part so that we don't have to. Here we go. Now I don't have to switch color of my pen anytime. Okay. So here, I will put the value. It is 78, right? And then as I mentioned, EDI, the value is also 78. And according to calling convention, RSI, or say ESI in this case, is 53. RDX, so E, it is, which is the third argument, which is 136. Okay, now let's continue. So the next instruction, it says move ECX ESI, right? So the value of ESI is 53, and then it moves to ECX. So the value of ECX becomes 53. Going to the next, we see there is a comparison. Compare EAX with EDX, and if EAX is greater than or equal to EDX, we're going to jump to greater. So here, EAX is 78, and then EDX is 136. So EX is not actually, it's not greater or equal to 136. So we're going to remain on the next instruction. So we need to continue from here. There's supposed to be a jump to greater, but because of the condition is not satisfied, we're going to stay here and go to the next instruction. So someone was asking me questions from chat. I'm checking it. I'm not quite sure the question of, should they be binary instead? If you can elaborate on your question, I'm going to answer you later. And EDX, those are the registers. And if you take a look at the video, you will be able to know what register are and what does those register mean. If you take a look at those EDX or ECX, they all represent different registers. Okay, now let's continue. So here, we're gonna add the value again from ECX to EAX. So this means that we want to do EAX is equal to EAX plus ECX. And then after that, we're going to subtract ECX from EDX. So it's going to be ECX is equal to ECX minus EDX. Okay. And then it jumps to the end in this return. Now the question is, what is the value of EAX and ECX, right? So let's take a look at it. The value of EAX and ECX currently at this stage is 78 and 53, right? So here ECX is going to be equal to 131. And in another case, which is ECX minus EDX. So the EDX value, as I mentioned, it's the third argument, so it's 136. So here ECX is equal to 53 minus 136. And you may be able to, you found that this is actually negative number, right? So this is actually negative 83. How can I represent a negative number in a register, right? Because register doesn't have a negative or positive value. So here, we want to convert it from a negative number to a signed number. And the way that we do it is to take a look at of ECX and notice that this is 32-bit for a register. So what we can do is to have 2 to the 32 and then minus 83, and we will get the value, get the answer. All right, now I suppose you know what is the actual result is. So the EAX is going to be equal to 131, and then ECX is going to be equal to 2 to the 32 minus 83. I'm not going to answer, I'm not going to calculate this, but you can just use Python to calculate this result. And I know that for each of you, the value of arguments for function assembly 0 is different. So for you, you may have a different flow of the program. You may actually go to the label of greater. And usually we call this different, going to different part of the function, we call this as a control flow. So we will say that a function that has a different control flow. And then we will say that for each of the program, or say for each of the function, we will need a control flow graph to represent how does this jump or going to the other instruction, how do those instructions actually connect to each other based on different kinds of conditions. So here, if we look at this code, we can just draw a very simple control flow graph based on the assembly over here. And what we could do for the control flow graph, what we could do is that we're going to use each node to represent the control flow that will only go single enter and single out. So in this case, if we start from the beginning, the first instruction of assembly 0, we can put instruction move EAX, EDI, and to jump. For this 4 instructions, we can put this 4 instructions together, because once you start from the beginning of this, groups of instruction, we will always end with the jump instruction. So if you draw the control flow graph of this binary of specific for this function, we'll be able to get move EAX. Actually, I'm gonna just use the assembly, the instruction address to represent each instruction. So it's B1, 9B3, and then into 9B7 together as one basic block. And this is called a basic block. Again, this is single in, single out. Okay, and then followed by that, we can, this basic block will answer to two possible directions, right? And one is to continue, which is 9B9, and then is gonna be actually, let me just write those out. 9BB followed by 9BD. And this is another basic block. Oh, give me a second. For some reason, my pen doesn't work. And I'm gonna remove this part. And let's continue. And then in another basic block is going to the greater part of the, right? So it's greater. So it's gonna be 9BF, 9C1, and 9C3. And then both of those two basic blocks go to the end instruction, which is 9C5. So as you can see, this is a graph for how the execution of assembly 0 can flow. And we call this a control flow graph. And this is very important for software security, or say for binary analysis. And later on, when you start to use, more advanced modern tools, you will see the control flow graph very, very often. So you don't really necessarily need to generate the control flow graph by yourself, but it will be really helpful for you to understand the meaning of control flow graph, so that in the future, if you look at the graph again, you will understand what it does, and you will get in useful information for you to do reverse engineering or vulnerability exploitation. All right. This is pretty much for this function, assembly 0. And I'm gonna track the questions on chat and see if there's anything that I need to reply or comment. Yep, I see some of you are asking questions in terms of Intel syntax. So for Intel syntax, it's always the operand, like the destination operand is in the left and the source operand is on the right. So this is different. Like this is a little bit counterintuitive. You see that the flow is usually from the right to the, like typical flow is from left to the right, but here in Intel, the move statement or say the add instructions, those instructions, the flow is from right to the left. But the nice thing for Intel syntax is that if you look at the comparison, and then look at JGE, like conditional jump, conditional branch, they actually follows the flow from left to the right. So the way that I like read, understand comparison and conditional jump is that I usually just look at the jump first and notice that this is GE, means it is greater than or equal, right? And then I'm just imagining that I put a greater than or equal sign in between these two operand. So I know that actually it's asking if EAX is greater than or equal to EDX. And if that is the case, it will jump to 9BF, the greater label. Right. And then again, in terms of negative value, because in a register, there's no negative over there, and you have to encode negative value to an actual unsigned value. And the way that you do it is to, use, you can flip them. It's like, if you have -1, it's gonna be F, 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 F. And then if you have a negative value, negative number, you want to do, 2 to the 32 minus the negative value. And the reason why we put 32 here is because EAX is a register with 32-bit. So we need to do 2 to the 32 minus the number. But if here is not EAX, say if here is RAX, so and if the value that RAX is representing for is a negative value, we want to do 2 to the 64 minus the actual number. Yes, so it's reading a signed number as an unsigned number. All right. Now, I'm going to move on to the next challenge. Actually, let's skip the next challenge and let's select another challenge. And let's work on this together. Let's take a look at, let me see, which one is good. Let's take a shift together. And I'm going to give you, again, like a 10-minute to go through the disassembly of function shift.
Professor?
Yes.
So I wanted to ask, actually already started the second challenge. So if I put in some random values and exit that challenge and go on to the shift challenge, will it allow me to go
Yes.
back to the second? Okay.
Yes, you can go back. Yes, that works.
Okay. Thank you.
Guys, so I noticed that some of you are asking questions in terms of the instructions or the operands in this function. So if you don't know what it means, that's totally fine. Like for me, I cannot know all the instructions, and some of them I don't know by myself as well. And the way that I do it is just to search it online. If you just search say you don't know SHL, what you could do is just like type SHL x6 64, and you can usually get the answer in terms of the instruction very quickly. All right, guys, time is up. Let's work on this challenge together. And again, before we read the instructions, let's figure out which syntax this assembly is using. So is this Intel or AT&T? This is Intel, right? Yes, because, again, there's no % showing for registers, so we suppose this is Intel. And always remember that if it's Intel, and for those move statement or arithmetic operations, the destination operand is the first operand. So it's always just move from right to the left and then add from right to the left. Okay, now let's start to read these instructions one by one. So the first one, and BR64. I don't know how many of you have heard of this instruction before, but this is a new instruction. And this instruction has a safety purpose. The reason why this is designed is because we, the compiler, or say the Intel, the CPU, they want to control the control flow of the the program. So in this case, they want to make sure that if there is an indirect call, which means that if there is a call saying call, say EAX or say like RAX, like this is a call, we call it indirect call. And the reason why is because here the register value, it can be changed. It can be equal to some arbitrary value, and even this value may be controlled by an input. So computers really want to make sure that once such call happens, it goes to a legitimate function, or it goes to a legitimate place. And that's why they start to put this mark and BR64 across programs. And so in the new compiler design, also the new Intel design, they start to have a flag that will be set once an indirect call is invoked. So it's like you can consider that as as a lock for call. And then after an indirect call is invoked, it will seek for the instruction of AND BR64. And this has to be happen right after an indirect call. So if this happens, that means that there is a lock, and this lock will be resolved by AND BR64, and we're all good. But if AND BR64 is not found, then it means that there's something wrong with this indirect call, and the execution will stop with an exception. In our case, we don't have to worry about call EX RAX, at least if we look at this part of assembly. So here we can just consider this as a no op for a call leave function. So there's no actual syntax change in terms of for this specific instruction. Okay, now let me just continue. So the first instruction, push RBP. So this is about stack operation, right? Now let's start to draw the stack. Again, this is a stack, and this is address high, and this is address low. So we push RBP, and that means that we're going to save the value of RBP into the stack. And usually, RBP before it calls before this function is called, RSP is the bottom of the stack. And now because we have push RBP, the bottom of stack RSP value will be changed as well. So now this is the new value of RSP, which points to the bottom of the stack. All right, and then next is going to be move RSP to RBP, right? And that means that we're going to move the value from RSP RBP, and RBP is going to point to this position as well. And the next is going to be subtract RSP by hex 10. So say RSP is going to point to somewhere lower. Oops, sorry. Let me redraw it. I wish there is a, oh yeah, here it is, undo. Good. Okay, now I'm going to remove this, and you see the new RSP and RBP. And usually for function, they have this preparation of stack, and they usually just do it by push RBP, move RBP, and the subtraction. So this is usually, this is a typical way for a function to start in order to prepare the stack properly. Okay, and now the next is going to be move the value of hex F to the address place of RBP minus hex 8, right? So reset this part is hex 10. So it's going to be saved in the middle. I'm going to just draw it over here. Hex 8, right? So say this is the place it's going to be storing hex F. Well, actually, so this is RSP, this is RX, this is RBP, and then this is RBP minus 4, RBP minus 8, and here is RBP minus C. So we want to store F over here, RBP minus 8. And then the next is move 0 to RBP minus 4, right? And next is going to move from RBP minus 4 to EAX. So the value here is 0, and it's moved, and it moves to EAX. So the current value of EAX will be equal to 0. And then EDX is going to be 1. And then move EAX to ECX. So ECX value is 0. And then we see there is a SHL. It means that it's shifted to the left, and it shifted to the left. It shift EDX to the left in the times of CL. And I got a question from the chat asking, what is the value of CL? CL represent for the lower register like the lower 8-bit of register ECX. So basically CL is associated with ECX. Here the value of ECX is 0, and then the lower 8-bit of ECX is also 0. And then here we shift EDX by 0 times. So here EDX value doesn't really change. And then move EAX from EDX. So EAX is still remain. Okay, EAX is actually changed to 1. And then we see we move the value of EAX to a new place, which is in the stack, pointed by RBP minus hex C. So here is the value. And then do a comparison. It compare EAX with the value that stores in RBP minus 8, right? Which in my case is hex F. So it compares this two, and if it's greater than, then it will jump to this place, hex 11C6. But in our case, it's not greater than, so we're gonna just continue.
Professor, can you repeat from the SHL command? After
Okay,
the SHL command, yeah.
So for this one, do you understand what SHL means?
Yeah, shift left, right?
Yes.
Mhm.
So here, the value of EDX becomes, the value of X is hex 1, right? So it's 1, right? Do you understand why the value
Yeah.
of EDX is equal to 1? Good.
Yes.
And then you
yeah.
move, yes, good. And then you move from EDX to EAX. So the value of EAX now becomes 1.
Yeah.
Okay. And then the next is you move EAX to the address that pointed by RBP minus C, right?
Mhm.
So if you look at the stack, this is the place that RBP minus C points to. So that's why we put the value of EAX, which is equal to 1, over here. Does it make sense?
Professor,
Okay.
how do you know that RBP minus C is in that location? Like,
So you know that because you draw the stack. Once you draw the stack, you know the value of RBP, and you know that this is the base value of the address, and then also the stack, the bottom value of the address, represented by RSP. So you know that between RBP and RSP, there are 10. Yeah,
okay,
there are 10 like positions, 10 bytes over there.
okay, sure.
Yep, and in that case, we can separate this hex 10 byte, which is like decimal, it's 16 bytes. We just cut it into 4 different small, like smaller chunks. And for each chunk, we're gonna fill it with value. So this is why when we do RBP minus C, we know this is the location, and then we just put the value of 1 over there. So,
Professor,
yes.
I have 2 doubts. Like, we have here used D word. Can you also tell what is Q word does? And if there are 10 locations, how does C comes into picture? Like, I'm a little bit confused on the addressing notation here.
Are you talking about the address notation in the instruction, like D word PTR?
No, no, the address location of this track, like how it is
Stack?
actually copied. Like, yeah, you wrote RBP, then you wrote RBP4, RBP8.
Yes.
Is it like moving by 4 and it's a hex 1, so that's why it's coming to RBPC?
Yes, it's a hex 1, so it goes to RBP minus C. So
Okay.
here is RBP minus 8 minus 4, right? So, and we know that the bottom of the stack, which is pointed by RSP, is there, like the distance between RBP and RSP is 16, hex 10. And then you know that here when we do move instructions, you point it to somewhere in the middle, and in the middle is here is hex 8, just like 8, and the other is minus 4. So you start to cut the part of the stack into 4 smaller chunks, and then you know that this is the place that you actually store the, the value of EAX2, which is RBP minus C. So it's like between -8 and RSP. And again, address is going from low to high, right? So RSP is the smallest, and there's only like 16 over there, 16 bytes over there. So if we do RBP -4, RBP -8 is going to be going down to some particular address.
And if it is keyword, then it will go up?
No, so keyword, it only means the numbers of bytes that you move. So it's not really because of the D word or keyword. That only means the width of copy, like how many bytes that you copy from one place to another. Here, the only reason why we do this is because we know that the pointer points at RBP -6 or minus RBP -8 and 4.
Okay, thanks, Professor. I got it.
Okay, so now let's continue. I know that we're running out of time. I will have a quick walkthrough for the rest of the code, and then I will let you know like this code's meaning so that you will be able to know what is the output of the assembly. All right, so continue. We are going to, we jump to this address, which is called, well, we should not jump over there because right now the value is smaller. So we should continue with this instruction, right? If we are greater than this, then we should go to 11C6, right? Which is this place. So you see that it's really just the end of the function. And here, if we continue with this, we'll look at, we'll find that there's another instruction that doing some shifting, right? We found that, okay, this is some value that we move from this place to EAX, and then it ends, and then end the value from EAX and this place. So basically, we found that what here really does is it has some value. EAX is equal to the value that stores over here in RBP -8 and RBP -C, right? And then moving on, we found that there again a shift to the left. Star is equivalent to SHL. So, and we found, where does this CL coming from, right? So CL's coming from above ECX, and then ECX coming from EAX, and then EAX comes from RBP -4. So basically what it does, it has EDX is equal to EDX left shift RBP -4. And then we do another move instructions, and we see here we do a print. So it means that it's gonna print some value. Use printf, so there must be a format string, and then followed by that format string, it must be some values over there. And in order to understand the value, like the format of printf, you need to look into the glibc function. And here, let's just move it very quickly. We found that, the register RDI, this is the register RDI, and it comes from RIP plus something, which is like from this hashtag. Hashtags gives you the address of this place. So this is the value, but we don't know it, right? I will tell you the value later on. And then the second argument is ESI. So ESI is from EAX, and then EAX comes from EDX, and then go back. We just like do this from bottom up. We'll be able to trace the value for those registers. So in reality, when we do reverse engineering, we don't really just like start from the beginning of the function or say a program and then read the instructions one by one, because as you see, if we do this, we have to understand every instruction. This is really time consuming. So instead, what we usually do is just like go to the interesting function or go to the interesting instructions. For example, like SHL can be an interesting one because it's related to arithmetic operation. Or say like a printf, it's also interesting because that means that it's going to output something. And then starting from there, we're going to trace back to those registers. We're going to get the values so that we can have a higher level understanding of the of the entire program. So really the goal is not to understand every line of the code or say every instruction. The high level goal for us to understand the semantics. In this case, because of the short of the time, I'm gonna have a hard stop over here, and I will give you the answer or say give you the hint for this specific challenge through Slack. And hopefully you can come up with this by yourself. And also I will tell you the information of this place, like the information of RDI later on Slack as well, so that you will know the format string for printf. And hopefully you can get this by yourself. And I will see you in the next week. Okay, I'm gonna stop recording.